How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at molecular shapes and the valence shell electron pair repulsion model. So our objectives will be to apply the VSEPR model of the molecules to determine and describe the shapes of molecules. So let's get going. Molecular shapes. So the Lewis structures are two-dimensional representations of these molecules. Now, if we have a two-dimensional molecule, like if it's linear, bent, or some sort of planar, the Lewis structure can accurately show the structure of the molecule. But it doesn't accurately show shapes for three-dimensional molecules. Like example here is methane, CH4. You can see the Lewis structure looks like it's just kind of like a plus sign almost, but you can see the molecular shape has three dimensions to it. So the Lewis structure doesn't accurately show you the true shape of the molecule. So let's get some terminology straight. First, we're talking about bond angles. Bond angles are the angles made by the lines joining the nuclei of the atoms in a molecule. So if I'm looking at this simple example of like H2, here we have a straight line. So the bond angle for a line is 180 degrees. So we'd say that would be the bond angle between those two atoms. Now in methane, which is a little more complicated than a hydrogen molecule, you can see here there's an angle formed. So when we're talking about bond angle, we're talking about the angle between these atoms. So other terminology, electron domains. So an electron domain is just a region in space where there are electrons likely to be found. So there's bonding electrons. That's one place, one domain, right? So bonding electrons are electrons that are shared between atoms. The region between those atoms is an electron domain. So you can see in this example of NH3, there's bonds with hydrogen and nitrogen, and that area between those atoms is a bonding domain, right? Then we also have non-bonding pairs of electrons. So electrons that are located principally on just one of the atoms. This represents an electron domain as well. So you can see nitrogen has these unshared pair of electrons. So that is another domain. That's another area where you're going to find electrons. So in this example, nitrogen has three bonding domains in red and one non-bonding domain in purple, right? So it has 4 electron domains total. So if the question was how many electron domains are there, the answer would be 4. If it says how many bonding domains, it'd be 3. How many non-bonding domains? Just 1. So VSEPR stands for Valence Shell Electron Pair Repulsion Model. And basically it's saying that electrons repel each other. So the geometry around an atom is going to be determined by minimizing these repulsions between electron domains. So for example, if I had a central atom with 2 pairs of electrons, well, they're going to repel each other. So they're going to spread out as much as they can to minimize those repulsions. If I had 3 electron domains around a central atom, they're also going to spread out in a way that's going to minimize those repulsions. Like basically it's going to try to get as far away from the other electrons as it possibly can. And that's going to dictate what shape these molecules make. So a useful way to describe the electron domains around a central atom is with ax notation. So it's like a shorthand so that you can communicate quickly how many bonding domains, how many non-bonding domains are there, right? It's a helpful way to keep track of these domains and the resulting shapes because of them. So A represents the central atom, X is the number of atoms bonded to the central atom, and E would be the number of unshared pairs of electrons. So with the example that I'm showing right here, the ax notation would be AX3E1, right? The subscript 3 tells me that there's 3 atoms bonded to that central atom, but there's also 1 pair of unshared electrons, right? So these would be the X's, there's 3 of them, and then this would be the E, and there's 1 of them. So it'd be AX3E1. So to start, let's just look at examples with only bonding domains. Kind of start there as a jumping off point. So you might want to try organizing your notes like this. I put a link to it. It will help organize the shapes and the geometries based on how many total domains there are, how many bonding domains are there, and how many non-bonding domains are there. But, you know, if you find that helpful, use it. If not, whatever. All right, so AX1E0 tells me that there is 1 central atom with 1 atom bonded to it. An example could be like H2. So the molecule is going to look like this. Now the bond angles for this molecule, you could probably guess if that's a straight line, bond angle is 180 degrees. And we call this geometry linear. Makes a straight line. So it's called linear. AX2E0. So Lewis structure, all right, we got two bonded atoms on a central atom. An example could be like CO2. What the molecule is going to look like is like this. So looking at this, what is the angle between these atoms? Well, it's 180 degrees again. Electronic geometry, still linear, right? Still a straight line. AX3E0 tells me there's three bonded atoms and no electron or unshared electron pairs. So an example could be like BF3. Now, when you make this molecule, you start to see, all right, if I look at it at different angles, I see different things. So if I'm looking at it from like bird's eye view, the angle between here, between these two atoms is going to be 120 degrees. And that's the same all the way around because this molecule is flat. It's planar. And it's a triangular shape, so we call it trigonal planar. Right? Plane just kind of means it's like flat. Everything's on the same plane. This makes a triangular shape overall, right? So trigonal planar. AX4E0, an example, could be like methane. It's got carbon as a central atom, 4 hydrogens bonded to it. Molecule looks like this. So you can see the molecular shape is different than what the Lewis structure looks like. So the bond angles here, it might not be so intuitive. You know, you might go, well, I can't tell what it is right there. It's 109.5 degrees. All right. So the electron geometry, we call this tetrahedral. So tetra means 4. And this shape has 4 faces, right? So if I take a look at the 3 hydrogens that are touching the table here, they form a triangle base. So we got a triangular base. And then we have triangles on 3 other sides, which is the shape of a tetrahedron. So it's tetrahedral. AX5E0. An example could be PCl5. And now this one starts to get pretty interesting, right? If we take a look at it from different angles, it looks like it has different shapes, right? This is not like symmetrically all the way around. But if we take a look, there is a triangle like along the equator. And then we have like a North Pole and a South Pole thing going on. So we got 2 different angles here. The angles between these atoms is different than the angle between these atoms. If I look at it on this shape, this angle is 90 degrees. Those atoms are 90 degrees away from each other. And if I look at it from this angle, you can see that, hey, those are 120 degrees away from each other. So we got 2 different bond angles here. So the electronic geometry, the shape that we're going to call this, is trigonal bipyramidal. You know, and it's not a super clever name. We have a triangle along the equator, and then we draw lines up to it, making kind of a pyramid. So we got a pyramid on top, pyramid on bottom, so it's bipyramidal. AX6E0. Example could be SF6. So the molecule looks like this, and if you look at it at a different angle, it looks like this. So now this one has the same bond angles all around, right? So the angle between there is 90 degrees, and it's 90 degrees all the way around. Now the electronic geometry, we call this octahedral. Again, oct means 8. So if you take a look, this has 8 faces, right? So if I'm looking at it this way, I have a triangle face here, and I have 3 more triangular faces around that because I have this kind of square equator. And then, so since I have this square base, when I connect all of the points, I end up with a pyramid on top that has 4 sides, a pyramid on the bottom that has 4 sides. So we call that octahedral. There's 8 faces. So electronic geometries versus molecular geometries. Examples so far have been when electronic and molecular geometries have been the same, right? That's where we started. So electronic geometries describe what shape do the electronic domains make. If I'm looking at all the domains, what shape is it? Molecular geometries can be different. They're trying to describe the shape that just the bonded atoms make. So what shape do just the bonded atoms make? I'm just looking at atoms. I don't care about those unshared electrons. You just ignore them. So now, if they don't have any unshared electrons, then the electronic geometry and the molecular geometry will be the same. So the total number of domains still dictates the overall shape around them, but the molecular shape just describes the shape that the atoms make. So if I take a look at this, right, I have a water molecule, right, and the notation here would be AX, well, there's 2 bonded atoms, and there's 2 electron pairs. So if I take a look at the electronic geometry, I have 4 domains around that central atom, so it's tetrahedral, right? Electronic geometry, I'm looking at all of the domains, the unshared pairs of electrons and the bonds between the atoms. Now the molecular geometry is saying, hey, ignore the unshared pairs of electrons. I'm just interested in the shape that the atoms make. You go, all right, well, how are we going to describe that shape? That shape's bent, right? We're looking at just the atoms. The shape that the atoms make would be bent. So let's take a look at some examples where we have unshared pairs of electrons. So AX1E1 means we have 2 domains total. There's 1 bonding and 1 non-bonding. So an example could be like nitrogen, N2. So here's what the molecule looks like. I'm going to say one of those nitrogens is my central atom. I have 1 bonded atom, so here's 1 bonding domain, but I also have an unshared pair of electrons. So I have 2 domains total. Bond angles on this, 180 degrees. It's a straight line, so the electronic geometry here is linear, and the molecular geometry is also linear, right? So even if I ignore those unshared pairs of electrons, the bonded atoms, there's 2 of them, still make a straight line. AX2E1, I have 3 domains total, 2 are bonding and 1 is non-bonding. So a Lewis structure could look at like SO2, and this is what the shape of SO2 looks like. And now you can see, all right, well the bond angles here would be, maybe you can tell it's 120, right? Because the electronic geometry is trigonal planar, right? If I'm looking at the atoms and the electrons, I have a trigonal planar shape. But the molecular geometry is going to be different. So molecular geometry, I'm ignoring these unshared pairs of electrons and I'm just looking at the atoms. And what shape does that make? Bent, right? That's the fancy scientific term for that shape, bent. AX1E2, still 3 domains, but this time we have only 1 bonding and 2 non-bonding. An example could be like O2. So you can see we have the 1 bonding domain, but then we also have 2 non-bonding domains. So the bond angles here, since I'm just looking at the atoms with bond angles, the angle between these 2 things is 180 degrees. Because even though it has an electronic geometry of trigonal planar, its molecular geometry is linear. All right? You can see how the atoms make a straight line, but if you look at all the domains, including the unshared electrons, you got a different shape. AX3E1, so 4 domains total, 3 are bonding, 1 is non-bonding. An example could be like NH3, ammonia. So you can take a look, the molecule looks like this. And the bond angles are based off of the electronic geometry. It'll be 109.5 degrees. All right, so if you go, what is the angle between these 2 atoms? You get 109.5 degrees. Because the electronic geometry is tetrahedral, whereas the molecular geometry is a little different. So if I ignore the unshared pair of electrons on top, I end up with a trigonal pyramidal shape. I have this triangular base, and they all come up to a point, making a trigonal pyramid. So molecular geometry here would be trigonal pyramidal. AX2E2, still 4 domains total. 2 are bonding, 2 are non-bonding. An example could be like H2O, and it looks like this. So now the bond angles are still going to be 109.5 because the parent geometry is still the same. The electronic geometry is still tetrahedral. But the molecular geometry here, all right, ignore the electrons and just look at the bonded atoms. It's bent. Bent with a bond angle of 109.5 degrees. Not all bent shapes will have 109.5 degrees. Some of them might be 120, but this one is 109.5. All right, AX1E3, 4 domains total. Again, 1 bonding and 3 non-bonding. An example could be like HCl, where chlorine's our central atom. Chlorine's bonded to 1 atom, but has 3 unshared pairs of electrons. So the bond angle here, since there's only 2 atoms, it makes a line. It's 180 degrees. The electronic geometry around that chlorine would be tetrahedral still because it has 4 domains total. But molecular geometry, just looking at the atoms, it's linear. All right, a note, special note, electrons are space hogs. All right, what I mean by that is they want to occupy more space than bonded atoms. So if I had an option, all right, where should I put these electrons? They can either go somewhere where they have 90 degrees of room or 120 degrees of room. Since electrons are space hogs, they're going to want to go where they have 120 degrees of room. So an example here is like I have 120 degrees between these 2 atoms that are like along the equator, or if I put them up here, then they'd only have 90 degrees of space. So where are they going to go? Well, they're going to go where they have more room. All right, they're going to go right here instead of up here. So they also repel the bonded atoms and distort the bond angles when they're not symmetrically around the central atom. So for example, here in our model, our perfect model, that doesn't account for that. We would expect this molecule to have 109.5 degrees as the bond angle. But when we observe the actual bond angles, you can see that these electrons kind of repel all those bonded atoms away from it a little bit more and pinches that bond angle to be something smaller. So, yeah, that's a thing. All right, let's take a look at examples with 5 total domains. This one, 4 bonding and 1 non-bonding. An example could be SF4. The molecular shape is going to look like this, and I've arranged it like this so you can kind of see what we're going to call this shape. So the bond angles, well, again, there's still 2 different bond angles. There's 120 degrees between these 2 atoms, but there's only 90 degrees between these 2 atoms, right? The electronic geometry, would be trigonal bipyramidal. And the molecular geometry, well, you know, what kind of children's toy does that kind of look like? A seesaw, right? You could draw, here's a kid sitting on it on one end saying, yay, and then the kid on the other side going, yeah, and it's like a seesaw. And you can take turns going up and down and then hop off on one side so the other person slams down. Maybe that was just my childhood. Anyway, all right, 5 domains again, this time 3 bonding, 2 non-bonding. Example could be ClF3. So again, the electrons are going to go where they have the most room. Instead of going at the poles where they have like 90 degrees of separation, they're going to go along the equator where they have 120 degrees of freedom. All right, so the bond angles here are only 90 because, you know, bonds are between atoms. So the only bond angles we have are 90 degrees. Electronic geometry is still trigonal bipyramidal, but the molecular geometry here is T-shaped. You can kind of see that we made a big old T, so it is T-shaped. All right, again, 5 domains total, 2 bonding, 3 non-bonding. Lewis structure example could be XF2, and the molecule is going to look like this. So again, the electrons go where they have more room, which would be along the equator. So if we're trying to describe the bond angles, again, we're looking at between the atoms, that would be 180 degrees. Electronic geometry is still trigonal bipyramidal because we still have 5 domains, but describing the shape of this molecule and just the bonded atoms, we'd call that linear. All right, moving on to 6 domains total, 5 bonding, 1 non-bonding. So AX5E1, Lewis example could be BRF5. Molecular shape is going to look like this. You see there's 5 bonded atoms and 1 electron pair. The bond angles are going to be 90 degrees. There's 90 degrees between any and all of these. The electronic geometry is octahedral. And then if we're trying to describe just the bonded atoms, well, we're going to call that square pyramidal, right? We have this square base kind of sitting on the bottom, and then all of those 4 points can reach up to the top, and we made a square pyramid. So the molecular geometry would be square pyramidal. 6 domains again, this time 4 bonding, 2 non-bonding. An example could be XEF4. So the molecule looks like this. Again, those electrons want to get as far away from the other electrons as possible. So why didn't we put the electrons over here? Well, then there'd only be 90 degrees between them. So the other pair of electrons get repelled all the way to the other side. Right, so that's why the electrons go where they go. So the bond angles here, again, would still be 90 degrees. There's 90 degrees between all of those bonded atoms. Electronic geometry, since we have 6 domains total, is still octahedral. But what about the shape of just the atoms? Well, if we take a look at just the atoms, we get a flat square shape. So we call that square planar. It's a square shape, and it's all on the same plane, square plane. 6 domains total again, this time 3 bonding, 3 non-bonding. Lewis, here's an example of what that would look like. Again, the electrons want to go as far away as possible from each other. This is the only shape they can make. Bond angles would be 90 degrees. Electronic geometry, still octahedral, but this time the molecular geometry, hey, we've seen this before. It's T-shaped. You can see the T there, right? All right, 6 domains, 2 bonding, 4 non-bonding. This is what it would look like. Again, those electrons are going to decrease their repulsions by all going around the same equator kind of thing. And we have 180 degrees as my bond angle because there's 180 degrees between those bonded atoms. octahedral electronic geometry because we have 6 domains, but the molecular geometry would be linear. All right, so why don't you try some practice? Draw the Lewis structures of the following and determine their electronic and molecular geometries. Pause it, see, give it a whirl, see how it goes. All right, welcome back. So if I take a look, BRF3 means we would have 28 electrons to place. So I'm going to put BR in the middle. I'm going to draw my bonds to fluorines. And then I got to finish putting the octet around the non-central atoms. And when I am done with that, I will have placed 24 electrons, which means I still have 4 electrons to place. So I got to put them around BR. So now the AXE notation around bromine would be AX, well, let's see, 3 bonded atoms and 2 electron pairs. So my electronic geometry would be trigonal bipyramidal, because these electron pairs are kind of going north and south, and then I have a triangle around the equator, so it would be trigonal bipyramidal. But the molecular shape would be trigonal planar, because it is a flat triangle when I look at just the bonded atoms. So the bond angles for this one would be 120 degrees. All right, NO2 minus 1 would have, let's see, 12 plus 5 plus 1 will be 18 electrons a place. So I put nitrogen in the middle, oxygen, oxygen, finish the octets for the oxygen, which would get me to a total of 16 electrons. So I still got 2 to place. I'm going to place them around this central atom. Now, I may have to make like a multiple bond here, but that's not going to change the geometry around this central atom of nitrogen. So for the AXE notation, well, let's see, nitrogen has 2 bonded atoms and 1 unshared pair of electrons. So my electronic geometry, well, let's see, 3 domains would tell me that it's going to be trigonal planar. But since one of those domains is an unshared pair of electrons, when I go to describe the molecular shape, it's going to be bent. Now the bond angles depend on my parent geometry of trigonal planar, which tells me that they will also be 120 degrees. All right, shapes of larger molecules, right? Oftentimes we'll be asked the geometry around a specific atom in a more complex molecule, and you just take the same approach and you isolate the central atom. So for example, if I had the CH3COOH, right? This is what the molecule looks like in real life. So if I were to describe the geometry around this carbon, well, let's see, I have 4 bonded domains around that one and no unshared pair of electrons, which would make this tetrahedral around that carbon, if I could spell. Now, around just that other carbon, well, this carbon has a double bonded O to another O. So around this one, well, let's see, there's 3 domains total, no unshared pair of electrons. So this one would be trigonal planar for both the electronic and molecular. Now this oxygen is bonded to a hydrogen, but it also has 2 unshared pairs of electrons around it. So its molecular geometry would be bent. And the bond angles for this bent would be 109.5 because the electronic geometry is tetrahedral. All right, so summarize. Can you apply the valence shell electron pair repulsion model of molecules to determine and describe the shapes of molecules? I hope so. Goodbye.